In module 1, we have oscillations and waves, and in module 2, interference and diffraction. The second chapter, waves, is actually a very small chapter, and in this video I am trying to cover about a half a portion of waves. In between I will be discussing a bit on oscillations and interference as well, because they are all interconnected. In the second chapter, waves, there is only one essay where you have to derive an expression for the fundamental frequency of transverse vibrations in a stretched string. Okay, first of all, what is a wave? You have to remember 3 points. First of all, a wave is a disturbance. Now, the second point is that the wave, it transports or propagates energy. And the third point is the wave does this transport of energy without the actual transport of matter. That is, the matter in the medium, it is not moving. It is just handing over the energy from one molecule to other. Next is types of waves. I think the types of waves you are most familiar with are transverse waves and longitudinal waves. A short question which is often asked for university exam is distinguish between transverse waves and longitudinal waves. Whenever you are asked to distinguish between two things in a question paper, you should write the answer in a tabular form like this. Instead of writing paragraphs, list out the important points as shown here. The first point is regarding the direction of vibration of the particles of the medium with respect to the direction of propagation of the wave. Suppose this is the direction of propagation of the wave. If the particles of the medium vibrate perpendicular to the direction of propagation, that is called a transverse wave. Now, if the particles of the medium vibrate parallel to the direction of propagation, then it is called a longitudinal wave. Even for the university exam, when we value the answer sheets of students, we often find that the first point is written like this, like the particles of the medium vibrate perpendicular in the case of transverse waves and parallel in the case of longitudinal waves. They won't write perpendicular to what or parallel to what. It is perpendicular to the direction of propagation of the wave or parallel to the direction of propagation of the wave. So do remember that point. Now, the second point is transverse waves can be polarized, whereas longitudinal waves cannot be polarized. Then the third point is one crest and one trough constitute a wavelength, whereas one compression and one rarefaction constitute a wavelength in the case of longitudinal waves. Now, give one example for each, that is electromagnetic waves for transverse waves and the sound waves for longitudinal waves. I think you must be familiar with this question, distinguish between transverse and longitudinal waves. You may have gone through this during your +2 classes. We can classify waves based on different criteria. One such criteria which we just studied is based on the direction of vibration of particles of the medium. If it is perpendicular to the direction of propagation, we call it a transverse wave, and if it is parallel to the direction of propagation, we call it a longitudinal wave. Now, another classification is whether it requires a medium or not. For example, mechanical waves and non-mechanical waves. Then based on the dimension of propagation, that is, if a wave travels along a straight line, it is called a one-dimensional wave. An example for it is the vibrations formed in a stretched string. If a wave travels along two directions, it is called a two-dimensional wave. Examples are ripples formed on the surface of a pond when we drop a pebble on it. Now, a three-dimensional wave, it is a wave which travels along the three directions. Example, sound waves, light waves, etc. Now, based on the duration of vibration, a wave can be classified as a pulse or a wave train. Among the different criteria based on which waves are classified, which I just discussed, a very important criteria is based on the dimension of propagation. If a wave propagates along a straight line, that is, there is only a propagation in one direction, we call it a one-dimensional wave. Example, wave propagation along a string. If a wave travels along a plane, that is propagation in two directions, then it is called a two-dimensional wave. Examples are ripples, then wave patterns formed on the surface of a tabla, etc. Now, if a wave propagates along all the three directions, then it is called a three-dimensional wave. Example, light wave, sound wave, etc. So, please remember this point. Now, characteristic properties of a wave. First one is wavelength denoted by lambda, then amplitude, time period, frequency, wave velocity. Then one more is there, it is called wave vector. Students often ask about wave number, nu bar. It is actually not a characteristic property of a wave because it depends on some other parameter, that is nu bar is equal to 1 by lambda. So it depends on lambda. So we can't call it as a characteristic property of a wave. In this slide, can you name the points which are in the same state of vibration as A? The correct option is the fourth one, AC, AE and AG. Similarly, here BD and BF are the points which are in the same state of vibration. Here XY and XZ, they are in the same state of vibration. PQ and PR are in the same state of vibration. Again, the set of points LM, LN and LO, they are in the same state of vibration in the upper half, and in the lower half HI, HJ and HK, they are in the same state of vibration. I hope you must have studied in your plus 2 classes that the distance between two crest or two trough is lambda. But now you know that not only the distance between two crest or two troughs are lambda, also AC, BD, LM and HI is also lambda. Now we can give a general definition for lambda, that is wavelength, as wavelength is the distance between two consecutive points in a wave which are in the same state of vibration. Instead of using two consecutive or adjacent points, we can also state as wavelength is the minimum distance between two points in a wave which are in the same state of vibration. What is the distance between two points in a wave which are in the same state of vibration? You know that lambda is the distance, or it is the minimum distance between two points, or it is the distance between two consecutive or adjacent points which are in the same state of vibration. Here they have asked the distance between any two points in a wave which are in the same state of vibration. The answer is n lambda. That is, if the distance between two points in a wave is n lambda, then they are in the same state of vibration, or we say that they are in phase. Now, what is the value of n? The value of n, it ranges from n is equal to 0, 1, 2, 3, etc. Here, a point is in the same state of vibration to itself. So, n is equal to 0 is also there. Now, what is the distance between two points in a wave which are completely out of phase? It is evident from the figure that lambda by 2 is the distance between two consecutive points in a wave which are completely out of phase. But they have asked the distance between any two points which are completely out of phase. The answer is 2n plus 1 into lambda by 2, or 2n minus 1 into lambda by 2. If you are writing 2n plus 1 lambda by 2, the value of n is 0, 1, 2, 3, etc. And if it is 2n minus 1 lambda by 2, you have to write n is equal to 1, 2, 3, etc. So if the distance between two points in a wave is 2n plus 1 lambda by 2, then they are completely out of phase. We will normally use 2n plus 1 lambda by 2 because here the value of n, it is 0, 1, 2, 3, etc. Whereas for the distance between two points which are in phase, also it is n lambda there, n is there also 0, 1, 2, 3, etc. Till now, we were considering the case of a single wave. Now we consider two waves. It is obvious from the figure that the first wave has traveled some extra distance when compared to the second wave. This extra distance we call it as a path difference. Now, the path difference between these two waves is 2 lambda as it is evident from the figure. When these two waves reach the screen AB, since the path difference is 2 lambda, they will be in phase. This you must have studied in your plus 2 classes. That is, if the path difference between two waves is equal to n lambda, where n is equal to 0, 1, 2, 3, etc., then the waves are said to be in phase. When we consider a single wave, we say that if the distance between 2 points in a wave is n lambda, then those points are said to be in phase. Now again, if the path difference between two waves is equal to 2n plus 1 lambda by 2 or 2n minus 1 lambda by 2, then the waves are said to be out of phase. Now again, if you consider single waves, we say that if the distance between 2 points in a wave is equal to 2n plus 1 lambda by 2 or 2n minus 1 lambda by 2, then those 2 points are completely out of phase. Again, you must have studied this condition for constructive interferences. Path difference between the waves delta is equal to n lambda, where n is equal to 0, 1, 2, 3, etc. And condition for destructive interferences is path difference between the waves delta is equal to 2n plus 1 into lambda by 2, where n is equal to 0, 1, 2, 3, etc. You have to remember this point. Now coming back to characteristic properties of a wave, you must be familiar with these definitions. First of all, wavelength denoted by lambda. It is defined as the distance between two consecutive points in a wave which are in the same state of vibration. Then amplitude denoted by small a or capital A is the maximum displacement of the particle from its equilibrium position. Then time period denoted by capital T. It is the time required to complete one oscillation or one vibration. Then frequency represented by either f small n or nu. We use the letter small n for frequency, and it represents the number of oscillations made by the particle per second. It is the reciprocal of time period. You may ask that nu bar, it is the reciprocal of wavelength, but we haven't included it as a characteristic property, whereas we are including frequency where it is the reciprocal of time period, because here frequency has a definition, it has a meaning. It is a number of oscillations made by the particle per second, whereas a nu bar, it is reciprocal of just a reciprocal of wavelength, and we often use it in spectroscopic studies to plot the graphs as a convenient parameter, nu bar. Okay, there. So it is not a characteristic property. Then wave velocity denoted by small v. It is the distance covered by the wave in 1 second. Now the last one is wave vector, which is not familiar to you by its name, but you have studied the same one by another name called propagation constant. Propagation constant k is equal to 2 pi by lambda. I hope you remember. Now this vector, it is a wave vector, it is a vector quantity, and it has got direction as well as magnitude. So we have to say about what its direction denotes and what its magnitude means. Now the direction of wave vector, it represents the direction of propagation of the wave, whereas the magnitude of wave vector, it gives the phase difference corresponding to unit path difference. We will see it in the following slide. Again, you must be familiar with this figure. The figure shows that uniform circular motion is equivalent to wave motion. Using this figure as a clue, can you say what is the phase difference corresponding to a path difference of lambda? The answer is 2 pi. That is, the phase difference corresponding to a path difference of lambda is 2 pi. Now, the phase difference corresponding to unit path difference will be 2 pi by lambda. And this 2 pi by lambda is we taking it as the wave vector k, the magnitude of wave vector k, it is equal to 2 pi by lambda. So the direction of wave vector represents the direction of propagation of the wave, whereas the magnitude of wave vector, it gives the phase difference corresponding to unit path difference. Okay, now coherent sources, it is a topic which comes in interference. So when do we say that two sources are coherent? It is a very important question and it's often asked in university exams. Two sources are said to be coherent if they emit continuous waves of the same wavelength or frequency and vibrate with a constant phase relationship. To vibrate with a constant phase relationship, we mean that the two waves either they should vibrate in the same phase or with a constant phase difference. A constant, that is, if there is initially a certain phase difference between the two waves, they should maintain that phase difference even after traveling any distance. So the important point is vibrate with a constant phase relationship. It means that is either they should vibrate in the same phase or with a constant phase difference. Now this equation is not familiar to you, and this equation is called the one-dimensional wave equation, or it is called the differential equation of a one-dimensional wave. Now you please get familiar with this one-dimensional wave equation and try to by heart it. It is dou square psi by dou x square is equal to 1 by v square into dou square psi by dou t square. Here please note that 1 by v square, and it is not 1 by nu square. Here it is v, the wave velocity v, 1 by v square. And here we have two second order partial differential operators, that is dou square in by dou x square and dou square by dou t square. So the left hand side the operator is dou square by dou x square. It operates on the function psi, and it is called the wave function psi. Dou square psi by dou x square is equal to 1 by v square into dou square psi by dou t square. This video was actually just a revision of what you have studied in your plus 2 classes. Important portions that you have to prepare from this video are distinguish between transverse and longitudinal waves, characteristic properties of a wave, definition for wave vector, conditions for constructive and destructive interference, what are coherent sources, then expression for one-dimensional wave equation. I will teach about this differential equation of a one-dimensional wave in the next video. As of now, you just by heart that equation. That is dou square psi by dou x square is equal to 1 by v square into dou square psi by dou t square.